little bit of the information that there is out there on the supply rates of magma coming into the volcano from depth. So we showed you guys this image before. This is an image from Professional Paper 1801, Chapter 5. This one's by Mike Poland. And you kind of see here our main SC, South Caldera magma chamber, our shallow chamber, and our east rift zone over here. Southwest rift zone, kind of an area we see it seismically deeper, and an area that the lava goes into shallower, kind of called a volcanic southwest rift. And our scale here, the surface 0, and we're looking at 10 kilometers below the surface. We have this, what they call basal decoma. This is this detachment, like kind of the bottom of the volcano, where it can kind of slide sideways. That kind of stack of magazines, the base of that big chunk of it. And I'll show you guys this a different view later as well. So let's go down to 10, and we also have the rift zones, which actually extend off of here like two big blades, right? Kind of like a long sleeves and a long robe here, right? Kind of that go down and call it a deep rift zone, where the magma can go in possibly more passively. Who knows from which directions exactly it's coming from, but they can kind of fill, as this whole south flank slides, it can fill that area. So we'll come back to that dynamic a little bit later. But so we're going to zoom out a little bit here, and this is an image from Professional Paper 1806, which is another one we've leaned on in the past. And now our scale on the left, our depth in kilometers, goes down to 40. So before we're looking at 0 to 10, and that 10 level of that basal detachment fault is now marked as this purple layer, right? Kind of at the bottom of the rift zone. So the rift zone kind of goes as far down as that. That's a dynamic there of how that interacts, and kind of 3D there, right? With a kind of main hot zone of magma flow coming up through one particular area in that, and kind of feeding it up that way, and then possibly this way, and then possibly you get some going down, and possibly you get some, you know, not quite sure, right? Exactly how that goes, but seems to be detached here at that 10 kilometers depth. And then there's actually the pathway that goes all the way down from 10 all the way down to 40 kilometers down to what they call this deep seismic zone. So this is an area of magma generation of the volcano. So let me kind of switch this over, and we'll look at this kind of quickly to show you guys that you actually can plot earthquakes. This is earthquakes from 1970 to 2007 under Kilauea. And the only thing different here is it's been separated by depth. 0 to 5 kilometers, 5 to 15, 15 to 20, 20 to 60, right? So kind of that's one way to look at it. We'll kind of zoom in on this inset over here where they actually stack them. You know, where did it go? Not sure what happened there. There it is. All right, they actually stack them. So here is our upper layer of 0 to 5 up here, and then 5 to 15, 20 to 60 down below over here. So you can kind of see that in a surface area, we see the pattern of the rift zones. Southeast, southwest rift zone is kind of an interesting southwest rift zone segment over there. You can kind of see that at the intermediate depth, 5 to 15, you see not the rift zone, but you see the south flank. And if you see towards the ocean from there, the south flank, right, with kind of a gap right where the rift zones go. Go down deeper to that 15 to 20 kilometers, and there's really not a whole lot there. It's actually an aseismic range for the most part, except for right at the core where it comes up. And when we get down to 20 to 60 kilometers, that's where you have that wider zone right there. If you kind of look at how it gets dense, it kind of goes off in that direction, right? That is the one that goes towards that deep Pahala zone. The earthquakes kind of connect in that kind of fashion to this layer right in here. So that's where we get that structure from. That's where this diagram comes from. And so there's our deep seismic zone down here, that upper detachment that separates the rift zones. And we have labeled here 3 reservoirs: upper reservoir, reservoir 1, as the upper right underneath the caldera, feeding the shallow eruption now. The deeper reservoir 2, the south caldera, and reservoir 3 is called this deep magma system. And so the authors of paper 1801 Didn't include this diagram. This one actually comes from Kathy Cashman et al. From last year, describing how these magma chambers may actually look in reality. Rather than drawing them as like a single blob, one big magma blob, you may actually have various kind of pulses that kind of come up when they're buoyant, and then when I reach some level of equilibrium, they will fan out and form a sill. So this is what we call a dike, the upwards, the vertical part of it, and the horizontal part of it's the sill. So dikes and sills. So when people say a dike and sill complex, this is what they're talking about, is this kind of thing. So this may actually be where you have your more liquid magma. You can have different pockets of different chemistries, and then you have this magma mush that's partially molten, kind of surrounding it and kind of connecting everything. So when it comes to earthquake waves, that's what you can see the edge of, is this outer mush layer. But you actually can have multiple batches of magma within there of different chemistries. Right, so they've actually, in this diagram, applied it to more continental cases and increasing SiO2, which is the stickiness of the lava, right? So all of our basalts are all at this end, and kind of mush and wall rock, and decreasing temperature as well. So these things will come into place, and then some parts might be cooler than other parts, depending on how recently they actually injected. So to kind of illustrate this effect of what's going on in here, but without having the benefit of this was published afterwards. These authors put in this kind of hatch mark zone right in here. I want to switch the color of my drawer, but can I see this hatch mark? That's our sill and dike complex all through there. And so they're kind of drawn schematically, kind of going starting in 1950 now. Different batches of magma that came up through the volcano at different times. And so you can kind of see that the magma that's going to erupt in 52 is this blue one, and that's what's shown coming up here. It comes up in blue in 1950, and it parks itself in that lower caldera chamber. It also puts a branch to the rift zone, and it parks itself there as well. So this is kind of setting the stage for what will happen later, 52. And meanwhile, you have the so we'll advance here. And so we can see that in the period of 52, we've now had 54 magma come in from below. This kind of reddish stuff is kind of just filling passively and filling the magma chamber through here. And then something that's going to come out in 61, Ma'u, already comes in 1950. And it sits possibly deep underneath the South Caldera, but mostly goes in the rift zone. So somehow it bypasses and doesn't really put a signal in the summit here so much. Our next increment from 52 to 54, we actually had an eruption in the caldera in 54. And you can kind of see here the red arrow showing that fairly quickly from depth, this patch came all the way up and erupted on the surface. Right, that's the kind of thing we don't have happening now. When we had our initial results of the magma chemistry, we learned that the magma we had coming out in this current eruption came out from having sat here for a while also, and then popped out. Similar to some of these other magmas that are coming up years ahead of time and sitting in the ground to feed the eruptions. So that's how it often happens, but sometimes, like in 54, you see it actually comes all the way up from some deeper depth and feeds that summit eruption and intrusion. Okay, we'll advance another increment here, the next year from 54 to 55. So in that time, that 61 lava is just sitting there in the main caldera, and it's also moving into the rift zone a little bit more and causing an intrusion over here under Kilauea. In the meantime, in 1967 to 68, lava will erupt 12, 13 years later, starts coming up in purple here, and we know it's going to park itself over here at some point, but it's also first going in the east rift zone over here. That's the next increment in time, so 54 to 55. That's that kind of period happening there. You can kind of see that it may be the pressure of this magma that eventually comes out in 6768 that goes in the rift zone. Over here in 1955, it's now the third magma body in the rift zone, right? So we have 67, 68 stuff will erupt. We have the 61 stuff that's going to erupt that actually popped up over here. We have the stuff at 52 erupted. And this stuff is moving up, and you can kind of see in 55, we're going to have a lower east rift zone eruption. It's going to happen as a result of all this rift zone taking these batches of magma. Okay, so from 55 to 1960, we have that purple batch coming up still. It's kind of filling the rift zone even more over here. Meanwhile, the 55 eruption is over and it's kind of still cooling underground. Some of that lava will get remobilized in 1960. But first, what causes 1960 to go off in the first place is this Kilauea lava. And that's coming from this black zone from way down at 40 kilometers down. And this is coming up. This is not exactly the path it took necessarily, right? This is like a vector showing where it started and ended with no known stops in between. So it may have come up along the side, but however it did it, it popped out of Kilauea and it was detected. And this is detected by those kind of earthquakes and by those chemical signals as well. So it came all the way up in 54. 60 to 61, you can kind of see that the black stuff ended up all the way to Kapoho, but it probably came up in a path Waiki and then back down to the rift zone, out of Kapoho that way. It's a more accurate path. But meanwhile, you see that the 67, 68 batch is now pushing up on the 61 batch, and the 61 batch finally erupts. In 61, it's the same thing that was intruded earlier, over under Kilauea. 67, 68 is that purple batch. Finally, that's been sitting under the summit for a while, but you have labeled down here what's going to be many magma batches coming from the mantle during the 5-year eruption of Mauna Ulu. And kind of that continuous increase in magma supply right there is going to be what pushes this batch of magma up. And so what we have going on now is probably not that unlike this, right? We had some of the magma that was in the summit went into the rift zone as well, right? There's probably some batch of it on the surface over here, right? But it's really the continuing pressure of magma coming from below, all these many, many batches from below, pushing what was here before up and out. And so depending how long the eruption actually lasts, you may see a progression of chemistry from what's been sitting here to what's been pushing it at some point in time. It might have to go on for months to a year for that to happen. But that's something that may be the case. Okay, so kind of a couple of other things to show you guys. This is a similar version for Pu'u. When Pu'u began in 1983, we had that batch of magma from depth coming in from the side, but there were 2 pockets of old magma, one from 77, that got mixed into that initial series of fissures before the more hot, juvenile, pure magma took over as a main source, and then eventually created that barrier, which is what kind of lasted until 2018. So even Pu'u had that similar kind of chemistry. And of course, we've discussed in the past the 2018 chemistry, how the lava that was feeding the lava lake drained out through the rift zone, past that blockage, and then came out in the lower east rift zone, pushing out perhaps 55 lava. Some older pockets, Fissure 17 might have been something from possibly 1790. There's also 1840. There's also 1924 as candidates in there. And other little pockets of lava, of magma kind of also all scattered through there, so who knows. So that's kind of the story, kind of rounding it out. But looking long term, scientists have looked at all these different patterns and they've come up with different rates of magma supply for the volcano over time. And so I've kind of compiled 2 plots here from a professional paper, and I've got 1823 back over here, and 2018 is off the plot over here. But the general pattern is we had very high magma supply back in the early 1800s, and it went down by around 1840 or so. So 1840 was a big caldera collapse, and that was, you know, an interesting shift, right? That kind of went down, and it stayed at a low level until around 1950 or so. And around then is when it starts going back up, and then really 2003 was when the latest batch of magma comes up to feed that summit lava lake, summit eruption, and eventually to 2018 eruption. That kind of begins back over here in 2003 was when that lava starts building up. So when you see a pattern like this, right, you might think, okay, well, maybe maybe really the only thing to compare to these high magma supply rates is anything that happened back before 1840, right? When we had caldera collapses in 1823, 1832, and 1840, but the previous two, with high supply rates, they refilled very quickly. We don't see much detail of that era in time, but we see the increments that we do see do seem to indicate that. And to kind of show you guys that, let me see if I have the right image here. No, this one. From Roadside Geology of Hawaii by Richard Hazlitt and Don Hinman. We'll zoom in here on these caldera maps, and so you can kind of see after the 1823 collapse, we have a deep pit in the middle, and by 1829, no more pit. That whole pit was all the way filled in. By comparison, our Halemaumau pit today is only maybe a third of that size. It's about this big, right? Whereas this earlier pit was the whole caldera, and the whole thing got filled in the next 6 years. So possibly there as well. You see 1832, the big pit is back. Another big collapse pit, but with kind of a big gap in time past 1840, we can kind of see it was refilled. In this case, you can't really tell how fast it refilled, right? But really, this sequence right in here, 1823 to 1829, shows you how much volume you could fill a big hole, how quickly. And we don't know if it was continuous or lots of small eruptions, and that's kind of where the big question mark is, what happened in those 6 years. But could be 6 years from now, we don't have a hole anymore if this thing goes at that similar kind of supply rate as we see back over here, right? 1823, here's the 2000s, yeah, even higher. And kind of explain a little bit more here. There's a little bit of blue on this diagram. The blue is trying to incorporate the south flank movement, right? So when the south flank is moving, like, is it actually, you kind of see the south flank starts moving more in this era, and maybe that leads the increase in magma supply a little bit, right? The south flank moves a little more in 1975, and magma supply rate after a little while increases more. I don't know. It's interesting to kind of look at those patterns a little bit independently, and that's why it's plotted on here as well. And each of these numerals is on here. So sometimes caldera collapse can change things a lot, right? This 1840 collapse maybe was caused by a drop in magma supply, but who knows, right? So that's why we don't know when we see a big caldera collapse, does it mean a drop in supply or not? And it seems like now, as this thing drags on, it seems more likely to me that we're kind of continuing this trend on this end. So how can we look into that a little bit more? Well, we can look at the ground tilt and GPS plots for the eruption of Pu'u. So Pu'u had been inflating, and then when it begins erupting in 1983, it starts deflating and deflates all the way until 2003. It's the first time it's actually switches course, and that's, if we go back to this graph that we're just looking at, 2003 is right here, right? So from 2003 onwards, higher supply rates. And you kind of see that as an initial pulse, and then a whole turnaround, and the whole trend of the graph starts going upwards until 2018, when it drops back down to eruption. Right, here's a GPS, similar plot, spreading, and then eruption right in there. So what happened past 2008? Well, the magma was still coming in at that high rate all through here. That's the evidence that we see, is we didn't see it turn around at any point in time. So since eruption began, actually ended in 2018, GPS has come back up, right, until we saw a little decrease now here. And so that's kind of what we're looking at as that pattern there. And that's why it's important to see if the GPS long-term is going down or is going up. Because if it's going up, then that tells us something maybe more about our supply rate and how long the eruption may last, compared to it going down, and maybe it won't last quite as long. So here's an image from a paper by Mike Garcia at University of Hawaii, Manoa. And he's kind of shown how our current configuration, when we have high magma supplies here on the left, we actually can have sustain two different magma chambers and an east rift zone feeder all at the same time. This was, of course, published prior to 2018, but you can kind of see that, right? You can have that much magma filling all that zone, whereas in the epoch of 1912 to 54, with low magma supply, you didn't actually have evidence of magma chambers. You had some eruptions that came all the way up and through and didn't touch any stored magma, and others that kind of came up and contaminated other later sources that came through them, and others that kind of went through some parts, then had different chemistries from then. So a lot less connected in the summit in those low supply times than in the high supply times. And so the fact that we do have still an upper shallow chamber and that lower chamber, and we still had magma filling the East Rift all the way to Pu'u, does put us more in a camp of this high supply rate still, an eruption lasting longer, or if it does end, that it will have another one shortly. It will kind of keep doing its thing, refilling on and on and on. So we'll kind of, that's the end of that. And let me